Okay, hi everyone, I hope your revision is going well. Obviously not too well as this year, the results might get standardised, so don't do better than me obviously. But anyway, yeah, so today is one of the challenge questions on one of the analysis sheets that the legend himself Jens Funke sent. Anyway, it's the integral from 1 to b of log x, right, but using log x as a regulated function. Okay, so our goal is going to be to find the area of the step function which converges uniformly to log x, and then take the limit as n goes to infinity, right? Because that's going to be this integral. Okay, so yeah, it'll make more sense when there's more writing down. Okay, so our goal is for the limit of the area of those step functions to equal b log b minus b plus 1. Okay, where did that come from? Okay, well, we already know what this is. Okay, so the integral of log x is x log x minus x. Okay, so when you have x log x minus x and you plug in those limits, right, you get that. Okay, so I couldn't be bothered to write it all out, so you know that's our goal, that's what we're trying to get to. Okay, so first of all, we need to define the step function that converges uniformly to log x. Right, so let's define the partition as follows. Let's define xk as b, or the nth root of b, to the power of k. Right? So we have the nth root of b, right? And then we're just going to raise that to the power of k, right? And when k is n, we're going to get b, and when k is 0, we're going to get 1. Okay, so let's write that down. So we have x0 is going to be 1, and b, well, that's going to be xn, right? And then we have loads of these, loads of points in between those partition points. This might be it, so this is going to be x n minus 1, and they're not equidistant, they're just randomly spread, but we have lots of nice points in between. Okay, and this is the graph of log x, right? And then we need to define what values the step function is going to take, okay, across these intervals, right? So just take fn. I'm just going to put that to my sheet. Okay, so first of all, so say we have some random point xk star, right, and this is going to be literally any point, and xk star is within, okay, so it's within the closed, bracket on the left, so we take it from xk to xk plus 1, but now we're going to have an open bracket. Okay, so this defines any point, right, any point in here, okay, except for b, but we'll consider that in a minute. So any point within here, well, it can be written as, it sits within one of these intervals, okay? Well, then let fn, okay, this is our step function of xk star, let it equal to f, okay, which remember was log x, okay, so I'll just say this is f of x. We'll let it be f of xk, right, and let's just rewrite that. So we have f is log x, so we have log of, well, xk was b to the k over n, so b to the k over n, right, and this is why we define the partition in this way, so that we can bring down the power. Okay, that's going to be very useful. We could have defined an equidistant partition, but this is going to be more useful. And then just define, okay, so this bit isn't very important, but we just need to do it for completeness. So define fn of b, okay, because b, b is the only point that can't be expressed as sitting within an interval. Fn of b, we'll just define that to be f of xn minus 1, which is, the height of log x at the partition point just before b. Right, so there we are. This defines a step function, right? And then we want to show that this step function converges uniformly to log x. Right, so we just need one more key detail. We need to find, let's just find the distance between each consecutive partition point. Okay, so the distance between xk plus 1 minus xk, right? This is going to be, well, just use the definition. So we have the modulus of, well, first of all, it's clear that the larger partition point is going to be bigger, than the one before it. Okay, so I can just drop the modulus sign, Okay, and this is going to be equal to, well, b to the k plus 1 divided by n minus b to the k divided by n, right, and then let's just neaten this up, so it's going to be b to the k over n, b minus 1. Right, again, let me double check. So, b to the k. Okay, this should be, this should be like that, right? So that's going to give us this thing, and then this times this is going to give us this, right? And that's a k, obviously. Okay, so this is the distance of each interval. Right, and then let's try and prove that this step function converges uniformly. Okay, so what do we need? So we have the modulus of f of xk star. Okay, so xk star represented any random point, so that's what we're interested in. And then, right, and then we're going to minus fn of x k star. Okay, so we want to find the difference between the step function and log x itself. Right, well, let's just use the definition of how we define the step function in the first place. Okay, so that's going to be f of xk star minus, well, we said that this was f of xk, right, up here. And this is all within the modulus. And then, what do we have? Okay, so we have, now it's nicer because we're not dealing with fn anymore, we just have things expressed in terms of f, right? But now, what would be very, very, very useful is if we could show that log x was Lipschitz, right? Because we want to relate this somehow to this. Okay, because it's clear that this can be made arbitrarily small. Right, as n goes to infinity, this goes to 1, this goes to 1 as well, so it's 1 minus 1, which is 0. Okay, so this can be made arbitrarily small. But this right now, well, we're not sure, okay, so we want to link it to this somehow. Right? So let's go, let's try that. So we want to show that this is Lipschitz, okay? Well, it's log x defined on a closed interval, right, from 1 to b, okay? So its derivative takes a maximum point. Okay, so log x, right, well, its differential is 1 over x, right, and that takes a maximum on this interval. Okay, it takes a maximum of 1, right? Because when when x is b, then 1 over b is going to be very large, relatively, and then when x is 1, well, 1 over 1 that's as big as 1 over x can get. Okay, that was probably a terrible explanation, but okay, so this is, well, it's less than or equal to 1. Okay, in this interval. Okay, so it's Lipschitz with Lipschitz constant 1. So we can just say that, well, this is less than or equal to, well, it's 1 times the modulus of xk star minus xk, right? And if it has a bounded interval, it's Lipschitz straight away, right? And you get that from using the mean value theorem. But I'm not going to go through that. So this thing is less than or equal to, well, the modulus of xk star minus xk. Well, xk star was defined to be any point within this interval. Okay, so the biggest distance that could be, the xk star minus xk could be, would be if xk star was, really close to this endpoint, okay? So this distance, well, it's strictly less than this thing, right? Because xk star sits within this interval, and then, well, this is equal to, well, it's b to the k over n, b to the 1 over n minus 1, and this can be made arbitrarily small, so this is less than epsilon. For any given epsilon, you can find a very large n for which this is smaller than epsilon. Okay, so I'm not going to write that all out. So we've proven that this step function converges uniformly to log x. Okay, so we found a step function that converges uniformly to log x, and now we want to consider the integral of log x. Okay, and that's going to be defined as the limit as n goes to infinity of our step functions. Okay, so the integral, okay, or the area under the strips of our step function, that's going to be the sum from 0 to n minus 1 of the length of each individual interval times the function value at that point. and the function value is constant between this interval because it's a step function. So the function value is defined to be, well, log of b to the k over n. Again, the length of the interval was up here, okay? This was b to the k over n times, well, the nth root of b minus 1. So b to the k over n times the nth root of b minus 1. Okay, we want to evaluate this. And then later on we're going to take the limit as n goes to infinity. Right, so first of all let's just bring anything that doesn't depend on k outside of the summation. Okay, so this is equal to, well, it's right here. This is equal to b to the 1 over n minus 1. Okay, and then I'm going to bring down this power. Right? And that's going to be k divided by n. I'm going to bring that down, but then I'll have log b, and that doesn't depend on k, so I can bring that out as well. So log of b, and then let's see what we have left. So it's still the sum from 0 to n minus 1, and then let's just put everything that does depend on k back in. Okay, so we have this, and then we have k over n, and this k over n came from bringing the power down from here. Right, and then, well, let's consider this. Okay, so I'm just gonna, well, first of all I'm gonna bring out this factor of 1 over n, and then I'm just gonna rewrite this slightly differently. So I have b to the 1 over n minus 1 times log b all over n, right, from bringing this factor of n out, and then I have the sum from k equals 0 to n minus 1 of, well, the nth root of b to the power of k times k. Then let's look at this and let's see what we can do. Right, we're going to try and evaluate this. Okay, well, this looks quite similar to differentiation. This is something that I've done before on the channel, because we have a power, and then we have a multiplicative factor at the front. Which is similar to the power, right? So let's try and force it to be exactly like a differential. Okay, so if I force out an nth root of b, okay, and now the powers are as we want. Okay, when we differentiate, we times down by the power and then decrease the power by 1. Okay, so let's bring this factor out. So I get b to the 1 over n times b to the 1 over n. Okay, just writing all this stuff. Log b over n. And then I'm going to rewrite this as the differential. Okay, so this is, well, it's the sum from n minus 1, k equals 0, of d by d, well, we could say, d by dx of, well, x to the k evaluated at the nth root of b, right? And then, well, when we have a summation, and we have the summation of differentials, we can bring the differential operator out to the front. Okay, so I can just switch the order of these, and I get, well, let me just rewrite that a bit neater. So this is log b, and I can bring the differential operator out to the front. Okay, so I have the differential of this thing evaluated at the nth root of b. Right, and then this is just, well, this is geometric now, so this is quite easy to evaluate. So we have this big thing, right, times, well, again, this is geometric, right? So we had x to the k. The common ratio is x, and our starting value is 1, right? When we plug in x equals 0, we get x to the 0, which is 1, okay? So I'm just going to rewrite all this as, okay, well, it's the finite geometric sum series. So we have a, which is 1, right, times 1 minus r. The common ratio was x, right, so 1 minus r to the power of n, right, divided by 1 minus r, which is x, right? And then obviously I can just rub out this 1, because that's not going to affect the thing. And this, again, is evaluated at the nth root of b. Right, and then let's just consider what the differential of this thing is. Okay, so we have this constant. Again, you know, I can't bother to just rewrite all these lines, but yeah, we have the differential of this thing. Okay, and this is just the quotient rule, right? This is, you know, standard stuff, so just treat it as u on the top and v on the bottom, and then the differential is vu dash minus uv dash divided by v squared. Okay, so let me just refer to my notes quickly. Okay, so when we have this, so this is equal to, well, this big multiplicative constant at the front, right? And then we have the differential of this thing, and I'm just going to write it out. Okay, so we have, well, this is all times by 1 minus x. Okay, so that's v times u dash plus, well, v plus v dash times u, right? And then you got to divide the full thing by this thing squared, so 1 minus x all squared, and this is evaluated at the nth root of b, right? And this is going to be, let's neaten this up, so we have b to the 1 over n over n. And apologies if this video isn't of the highest quality. I mean, I just wanted to get this out before the analysis exam, because I mean, there's no point in putting it out before. So yeah, sorry that it's not like, you know, the most entertaining or of high quality. But anyway, we move. So let's sub this in. So we get 1 minus nth root of b. Okay, and obviously this is times. Okay, times minus n, and then it's b times b to the n minus 1 over n plus, well, when we're subbing the nth root of b here, I get, well, 1 minus nth root of b to the power of n, that's going to be 1 minus b. Okay, and then this is all divided by 1 minus b to the 1 over n squared. Okay, so I've rewritten everything that was here up at the top. And now we want to take the limit as n goes to infinity of this thing, right? But we have two distinct parts of this expression because of this plus sign. Okay, so in reality we're taking two distinct limits. Okay, so let me just distribute this factor across to this thing and across to this thing. Right, so first of all we have b to the 1 over n divided by n times b to the 1 over n minus 1 times log b, and then times this entire thing. Okay, so we have 1 minus b to the 1 over n times minus n. Okay, but let me just distribute that minus over here. Alright, so I have 1 minus nth root of b. Okay, times b to the n minus 1 over n, and then all divided by this thing. Right, so all divided by 1 minus b to the 1 over n squared. Right, now let's do the same thing with this part. Okay, so hopefully it's not as messy. So we get plus, well, let's do the same thing. So we get b to the 1 over n, b to the 1 over n minus 1 log b, and then times this thing. Right, times 1 minus b, and then all divided by 1 minus b to the 1 over n squared. And that is the sound of the taps that I also get at like 4 AM in the morning. Anyway, yeah, so that's what we get. Yeah. So now let's do some cancellations. Right, well, on the denominator, this denominator is going to cancel with this bracket times this bracket. Okay, so I can literally just rub that out. Again, taps. Thank you, Laura, if you're watching this video. I'm only joking. So yeah, we have n, and this is going to cancel with this n, right? And then let's just combine these two powers. Okay, so we have b to the n minus 1 over n, and then I have b to the 1 over n. Okay, so if I just add the powers, well, I'm going to get plus 1 over n, and, well, you know, the ones are going to cancel, I'm going to get b to the n over n. Well, that's just b. Alright, that's just b to the power of 1. Okay, so b to the n of n, which is b to the 1, which is just b. Right, and now we see that this is independent of n. So I don't actually need to take any limit, there's no limit that's been taken here. But I need to take the limit as n goes to infinity of this thing. Alright, well some things don't depend on n. So let's take whatever doesn't depend on n, let's take that out. So, but before we do that, let's cancel these two terms. Okay, so it's going to introduce a minus sign because this is the same as minus 1 minus b to the 1 over n. Okay, so let's distribute this minus sign here. So b minus 1, so I've distributed minus sign here, but then I need to, of course, have another minus sign so that I'm only timesing by 1 and I'm not affecting, the actual value, if that makes sense. Minus 1 times minus 1 is 1, so I haven't actually done anything here, that's what I'm trying to say. And then cancel this bracket, because it's no longer squared, and I can just worry about this thing. Okay, and then let me just bring this thing over here. Right, so I have log b, I can just rub that out, and then I have b minus 1, and I'm just going to rub that out. And that's because this doesn't depend on n, so when I take the limit, it's kind of irrelevant. Alright, and I'm just going to rewrite this n, instead of being on the bottom, I'm going to rewrite it as being on the top. Okay, now we see as we take the limit as n goes to infinity, we're going to have something of the form 0 divided by 1 minus 1, which is 0. Okay, a limit of the form 0 over 0. Right, easiest rule to apply is L'Hopital's. Okay, but it's going to get a bit messy because we have 1 over n. So it'd be nice if we made a nice substitution. Right, so let u equal 1 over n, and then, well, as n goes to infinity, u is going to go to 0 from the right. Okay, because it's positive infinity. So let's take this limit, right? And of course that's a times sign here. Right, so now let's take the limit. Okay, so as I said, this is independent of n, so it stays as it is. So we have b log b plus this factor. Okay, and then first of all, let's consider what happens to this b to the 1 over n. Okay, well, let's be very pedantic. Let's sub in the u, so we get b to the power of u. And then as u goes to 0, we get b to the power of 0, which is just 1. So I don't actually need to consider this thing. This is kind of irrelevant. This is not the dangerous part. The thing of the form 0 over 0, that's the dangerous part. Okay, so ignoring this, now apply L'Hopital's rule to this fraction. Okay, so let's make our substitution times the limit as u goes to 0 from the right of, well, u, which is 1 over n, divided by 1 minus b to the u. Right, now let's apply L'Hopital's rule. So, this thing, unaffected, doesn't depend on b. Plus, no, this is just a multiplicative constant, I cannot say that word. And then let's take this limit. So we have the differential of the thing on top. This limit as u goes to 0 of the differential of the thing on top, which is 1. And then the differential of the thing on the bottom. Okay, so we have the minus sign, and then we have log b times b to the u. Okay, then you can just sub in 0 here. B to the 0, that's just going to be 1. So this is equal to 1 divided by minus log b. Again, we're going to get some nice cancellations. So this log b is going to cancel with this log b. And then all I need to do is distribute the minus sign. So let's just distribute the minus sign here. So I get minus b plus 1. Right, when I distribute the minus sign. Okay, and this was our goal. This video has taken me so many takes, and I should probably get back to doing some real work. So yeah, this video is very messy, but if you did enjoy, then good for you. I hope the exams do go well, and yeah, I'll see you next week when the quality of the videos are going to be back to normal and I'm slightly less stressed.